Okay, thank you for the introduction. And first of all, I would like to thank the organizers for giving me the chance to speak here today. In this talk, I will try to explain a little bit work we did last year as part of my PhD studies, which consisted of the description of homogeneous manifolds with half-harmonic biocurvature in dimension 4. When I thought of this talk, I thought of making it as brief and clear as possible. So I will try to do it. I'll do it the best I can. So the idea is to give some context to this study first and give some examples of the main definitions of this work. And after that, I will try to explain a little bit of our procedure to make this description and this classification and show you the main results of this work. So just let's start by saying what half-harmonic biocurvature means. If we have a Riemannian manifold, we say it has harmonic biocurvature if its divergence vanishes. We chose to use the first divergence, but we could have used fourth or whatever. And to give some examples of this, any Einstein metric has automatically harmonic biocurvature. So this condition has been broadly investigated in order to extend geometric properties of Einstein metrics to more general structures. Another example for this are locally symmetric Riemannian manifolds, which also have harmonic biocurvature, and it is known that the converse is also true in the four-dimensional homogeneous setting. We will see that this is not true anymore when we talk about half-harmonic biocurvature, which is what we are going to do now. So what is to have half-harmonic biocurvature? The thing is that it is known that the Hodge-star operator induces a decomposition into the space of two forms into its self-dual and anti-self-dual subspaces, which are the eigenspaces associated to the plus and minus 1 eigenvalues of the Hodge-star operator. And this decomposition in the space of two forms gives rise to a decomposition of the biocurvature into its self-dual and anti-self-dual parts, which are the restrictions of the biocurvature into each of these two subspaces. Given this decomposition for the biocurvature, its divergence decomposes accordingly. So we have this expression you can see there. And if we have a Riemannian manifold, we say it has half-harmonic biocurvature if either of these two components vanishes. This condition has been investigated during the last decade in order to describe different classes of Riemannian metrics, such as Ricci solitons, or even quasi-Einstein manifolds. In our study, the condition we focused on is the first one, but we could have used the other one anyway. The result would be the same. So let's give some examples about this. It is known that the geometry of four-dimensional Kähler structures is much reflected into its self-dual and anti-self-dual Weyl curvatures. In fact, the Wagner tensor is codified by the anti-self-dual Weyl curvature, and this way, this condition of half-harmonicity is equivalent to weak Wagner flatness. And moreover, it is known that any weakly Wagner flat Kähler manifold with a constant scalar curvature is locally symmetric. So all of them have harmonic Weyl curvature. So they automatically are half harmonic anyway. And moreover, we know that any four-dimensional Kähler manifold with non-vanishing self-dual Weyl curvature is conformal to a metric with half-harmonic Weyl curvature. So now let's restrict our study to the four-dimensional homogeneous setting and say that Berard-Bergerie showed that any homogeneous, four-dimensional homogeneous Riemannian manifold is either symmetric or a Lie group endowed with a left invariant metric. As for the symmetric situation, we have already talked about this. Every one of them have harmonic Weyl curvatures. So this situation will not give strictly half-harmonic examples. So we left this out of our study and just focused on the Lie groups. And in four-dimensional Lie groups, we have these 6 possibilities here. So this, there should be a tilde here, but I don't know why it's just half a tilde, sorry. But, okay, so let's focus on these 6 Lie groups. The first thing we need to notice is that the last 3 of them admit an orientation reversing isometry. So the moment one of them verifies one of the conditions to have half-harmonic Weyl curvature, automatically satisfies the other one. So this one will never give a strictly half-harmonic example, so we also leave them out of our study, and we focus in these 3 Lie groups. Now I will just take the last of them, the semi-direct extension of the Heisenberg group, to illustrate our procedure to classify these structures. So following Milner's work, and given the expression of the algebra of derivations of the Heisenberg Lie algebra, 3-dimensional Heisenberg Lie algebra, we know that the Lie brackets can be written in this way, where we have 6 constants, and we know that gamma is not 0. So just a parenthesis here, since we are working with Lie groups and we restrict to the Lie algebras and we work with the 0 to Weyl curvature tensor. So in order to compute the anti-subdual and the self-dual Weyl curvatures, we use these expressions you can see here where the EIs, the elements of the basis, satisfy these conditions you can see there. So if we now compute the divergence of the self-dual Weyl curvature, we see that it is given by that the components of this divergence are given by certain polynomials up to some constants. So the thing we can see here is that the problem to describe all the metrics that are half-harmonic just consists of solving a system of polynomial equations, so easy. But maybe not so easy because the polynomials are these ones, but we will see that it was not as difficult as it could seem at the first sight. So, but yeah, first you find this system of polynomial equations and you say, okay, what can I do with this? First thing I can think of is that I know that gamma is not 0, so I can just change the basis considered, that one you can see there, and assume for the rest of my computations that gamma is 1. But it is still too complicated. I have 5 unknowns here. So what can I do? So the thing we did was ask for help, and we asked Grabner basis for help. For those who don't know how Grabner bases work, if we have a set of polynomials belonging to a certain ring of polynomials, and an A and N tuple of real numbers, I know how to pronounce it. Okay. If A is a solution, a root for every of the polynomials in our initial set, then A is a solution for any polynomial belonging to the ideal generated by this polynomial thing here. And the interesting thing is that if we can find some different polynomials generating the same ideal as the first polynomials we had, then A will also be a solution for this, and conversely. So the idea is to find somehow simpler polynomials that allow us to solve this system of polynomial equations. And these QIs is what are called grounded bases, the set of all of them. These grounded bases can be huge, but I mean, they may have a lot of polynomials. But the important thing is to find just one that gives us a hint to solve the rest of the equations. So how do we do it? It's all computational work, but we only need to fix an order for the variables, and then it's just running the program. But okay, so let's do this with our system of polynomial equations. We know that this system, all these polynomials belong to that ring of polynomials, and we fix the lexicographical order of the variables. The Grobner basis is not that we found is not huge, but it was pretty big. But the important thing is that this polynomial in here, I don't know if you can see it, belonged to that basis. So this automatically shows that h has to be 0. And from this point, everything goes straightforward. Because these two polynomials that belonged to the first set we had reduced to this expression in here, and the first one just automatically says that f has to be 0. And from this, the second polynomial just gives two possibilities for a and d. So now for the first case, we have that one of the polynomials just takes this expression, so we have these three possibilities for the value of a. And in the other case, we have that this sum of the polynomials has that expression there. So, whoop, what just happened? Okay. So this gives two possibilities for a and d. Okay, so our huge system of polynomial equations seems to have 5 solutions, but studying there a little bit more, we see that we can forget about this one because it gives rise to an Einstein metric, so it is automatically harmonic, so it does not give any strictly half-harmonic examples, so we forget about this one. And these other two are equivalent through a change of coordinates, so you just need to interchange E1 with minus E2 or something like that. So we just need one of them. So our pretty big system of polynomial equations just gives two non-symmetric solutions which are homothetic to these two I show you here. As for the other two Lie groups I left behind, again we find a huge system of polynomial equations, and proceeding in the same way we get to no non-symmetric solutions. So we only find strictly half-harmonic examples in that semi-direct extension of the Heisenberg group. So I think I went too fast, but anyway. Our main result just is very simple. It's that any four-dimensional locally homogeneous Riemannian manifold with half-harmonic via curvature is either symmetric or a semi-direct extension of the Heisenberg group, give to one of these two possibilities. It's homothetic to one of these possibilities. Just say that the first one is anti-self-dual, and it corresponds with the one given by Salomon and Diaz-Met, I think. Moreover, they are locally conformally Kähler and Ricci-flat, so they are quasi-Einstein. And moreover, if you compute the back tensor, you find this is 0 everywhere, so they are automatically steady back solitons also. As for the second one, this is Kähler and opposite almost Kähler. So this corresponds to the four-dimensional three-symmetric space. And I say the four-dimensional three-symmetric space because Kowalski proved that there is only one four-dimensional three-symmetric space and gave an expression to it both in coordinates and as homogeneous space. This metric is also an algebraic Ricci soliton, which is expanding, and it's also an algebraic back soliton. And none of them are gradient solitons because the underlying structure for this metric is not that of a product, so we cannot have that. And yeah, I went so fast, but this is everything I wanted to tell you, so thank you very much for your attention.